Hello, my name is Ahmed Taha. In this video, I'm going to present how Fully Sharded Data Parallel works. Fully Sharded Data Parallel, or FSDP, is not a difficult topic, but a new terminology is needed to understand it. So during this presentation, I will first cover new definitions, then I will recap how Distributed Data Parallel, or DDP, works as a warm-up, then I will focus on Fully Sharded Data Parallel. At the end of this presentation, I will list some reason when to use FSDP and when not to use FSDP. First, we need to understand what is stored inside the GPU memory when training a deep network. In this presentation, I will focus on the parameters, their gradients, and the optimizer state. It is important to mention that intermediate features and activations are also important and reside in the GPU memory. These are needed for backpropagation and they actually take much larger GPU memory. But for this presentation, I'm going to focus on the model itself and the optimizer state. I'm going to use Adam Optimizer to compute the memory needed by the optimizer state. Adam Optimizer takes a copy of the model parameters. These are the trainable parameters. For simplicity, I'm going to assume that all the model parameters are trainable. Beside the trainable parameters, which is the weights, Adam Optimizer keeps track of two more variables. These are the momentum and the variance of the gradient, which is computed during training. Fully sharded data parallel is used to train large models. These large models are typically trained using mixed precision. So I'm going to assume that we are using float 16. Now we have all the needed details to compute what resides inside the GPU memory. For every parameter x, we will need 2 bytes, assuming float 16, to store this parameter, which we are going to use during feed forward. We are going to also need 2 bytes to store the gradient for every parameter. Even when we are training using mixed precision, the optimizer state is always stored in full precision, which is float 32. So for every parameter, we will need 4 bytes to keep track of that parameter. We will also need 4 bytes to keep track of the momentum and another 4 bytes to store the variance. These are all stored in float 32. Basically, the optimizer, Adam Optimizer, uses 12 times the number of parameters. This figure illustrates how our GPU memory looks like when using Adam Optimizer. In this figure, we are training a model with 7.5 billion parameters. We are doing so on 64 GPUs in parallel. The first row here, we are assuming that there is no sharding at all. The memory consumed will be 2 plus 2 plus k, 2 bytes for the parameters, 2 bytes for the gradient, and k bytes for the Adam Optimizer state. The model parameters are displayed in blue, the gradient in orange, and the optimizer state in green. I hope it's clear now that the optimizer state is taking a lot of memory. By sharding our model across nodes, we can reduce the memory consumed. For instance, if we shard the optimizer state only, the consumed memory will go down from 120 gigabytes to 31 gigabytes. We can reduce the consumed memory further if we shard the gradient and the model parameters as well. Now that we have illustrated what resides inside the GPU memory, I'm going to review how distributed data parallel works. I believe understanding how DTP works is the key to understand how FSDP works. But before delving into DTP, I need to make a small detour and present NCCL first. Don't worry, it is a simple library. NCCL is a library developed by NVIDIA. NCCL is short for NVIDIA Collective Communication Library. This library provides primitive functions optimized for multi-node communication. Example for these primitive functions can be all gather, all reduce, etc. I will give a concrete example to better understand the NCCL library. Let's say I'm running a program on multiple nodes. While I'm running the same program on all these 4 nodes, every node is processing a different split of the input data. Accordingly, every node will compute a different result here, like in blue, red, green, and yellow. Now, what I want to do is that I want to aggregate or reduce these different results into a single node, which I'm going to call root. The NCCL library provides a function called reduce to achieve this goal. Inside every node, we can call the NCCL reduce function, provide the results that we have computed as an argument, as you can see here. We should also provide the root node where these different results will be aggregated or reduced. The NCCL library provides multiple reduce operations. For instance, we can sum these different results across different nodes, or we can take the average or take the product. Most importantly, the NCCL will take care of all the communication between these multiple nodes and make sure that the root node will receive the correct result. Besides the reduce function, NCCL provides all reduce which is used in distributed data parallel. And instead of reducing the result from the multiple nodes to a single root node, the OReduce function reduces from the multi-node to all the nodes. In distributed data parallel, we are training on multiple GPUs, and all GPUs have the same weights. But every GPU processes a different mini batch. So every GPU will have a different loss value, and after backpropagation, every GPU will have a different gradient array. Now it's important to aggregate the different gradient from all the GPUs. So after the optimizer step, all the GPUs will have the same weights. I want to recap this point again because it is important to understand how DDP works. At the beginning, all GPUs will have the same weights, but they are processing different mini batches. So every GPU will proceed forward with a feed forward, and then it will compute the loss, do a backward propagation, and compute gradients locally. At this point, every GPU has its own local gradient. So we will call OReduce to aggregate the gradients from all these GPUs. This will make sure that all GPUs have the same global gradient. Now, once we have this, we can now update the optimizer state and the weights locally. Nothing is new in this slide. It just demonstrates how distributed data parallel works using these figures that I took from a Facebook blog. It starts by having the same shared model across different GPUs. Every GPU will make a local forward pass, then a local backward pass, then all the GPUs will call OReduce to aggregate the different local gradient into one global gradient. That one global gradient will be used to update the weights of our model, and then we return to our initial state where all the GPUs have the same weights. Now that we have reviewed the NCCL and DDP, it is time to explain how FSDP works. Before explaining FSDP, I want to make sure what is not FSDP. There are multiple model parallelism techniques in literature. They are similar to each other, and it is easy to mistakenly call them FSDP, and I want to make sure we don't make this mistake. In DDP, we split the mini batch across GPUs, but every GPU have the entire model. In model parallelism, we split the layers of our model across GPUs. In this example, layer number 1 will reside on GPU number 1, while layer number 2 will stay on GPU number 2. During the feed forward, we have to manually move the data to GPU1 and then to GPU2. While this approach reduces the GPU memory needed by our model, it is inefficient because while GPU1 is processing the mini batch, GPU2 is doing nothing. GPU2 is just waiting for GPU1 to process the mini batch, and the same problem happens during backpropagation. Tensor parallelism is another approach to reduce our model's GPU memory, but instead of splitting our model vertically, we split it horizontally. This way, both GPUs will work in parallel that is, GPUs are not waiting for each other. This example illustrates how tensor parallelism works. Let's say we are doing matrix multiplication. This is our data, and this is the weights of our layer. We split the weights of our matrix on two GPUs. In this example, every GPU will be responsible for one column of our matrix. We multiply our data with each column on each GPU independently, and to get the final result, we simply concatenate these together. Another approach to reduce a model's GPU memory is pipeline parallelism. Recall that model parallelism splits the model vertically and GPUs wait for each other. So when we feed the mini batch to the first GPU, that GPU do its feed forward, and then the output of the first GPU will go as an input to the second GPU for its local feed forward, and so on. This is of course inefficient because GPUs are waiting for each other. Accordingly, pipeline parallelism has been proposed to mix data and model parallelism. Pipeline parallelism is optimized so that GPUs can work together in parallel. So while the second GPU is processing the output of the first GPU, we feed another mini batch to the first GPU. This way, GPUs work in parallel, and this reduces the waiting time for each GPU. Now that we have presented all the needed background topics, it is time to dig into FSDP and how it works. FSDP has four key parts. First, there is a FSDP unit, which can be regarded as a vertical splitting of our model. Then there is sharding, which can be regarded as a form of horizontal splitting. Then there is all gather and reduce gather. I will cover these parts in details in the next slides. FSDP starts by splitting a model vertically into units. Each unit can contain a layer or a stage or a group of layers. The constructor of SDP model allows the programmer to decide how to create these units. During this presentation, I will use the example on the right-hand side. In this example, our network is broken into three different FSDP units. Unit 0 contains layer 0 and layer 3, while unit 1 contains layer 1 and layer 2, and same thing with unit number 2. After splitting our model into FSDP units, the next step is sharding. Sharding starts by storing the parameter of the FSDP unit into a structure called flat parameter. Then we shard this flat parameter on our GPUs. Basically, each GPU will maintain part of this flat parameter structure. This figure here demonstrates this idea of flat parameter and sharding. Let's say that we have an FSDP unit that contains 12 weight terms and 3 bias terms. We also plan to train our model into 16 GPUs. First, we create flat parameter, a structure that contains all our parameters. In this example, we have 15 parameter only. This is 12 plus 3. This number is not divisible by the number of GPUs. So we zero bad the flat parameter, so it is divisible by the number of GPUs. Once we have created that flat parameter structure, we shard it across our GPUs. In this toy example, each GPU will get a single element, and from now on, each GPU will be responsible for its own part of the flat parameter. This is another figure to illustrate the idea of sharding. The first row shows a distributed data parallel DDP example where each GPU maintains a copy of the entire model. In the second row, we are using FSDP and we sharding the optimizer state only across GPUs. Once we have done the sharding, each GPU is responsible for its own set of parameters. The third and the fourth rows show another sharding strategies. For example, we can shard both the optimizer state and the gradient. When creating our FSDP model, we provide through the constructor what sharding strategy to use. Based on this parameter, we can shard the optimizer state only, or we can pick another sharding strategy and, for example, shard both the optimizer state and the gradient as well. Now that we have defined our FSDP units and sharded our model across GPUs, it is time to start the training process. To do so, we will need to use all gather. We will use this operation during both forward and backward passes. So let's dive into it. AllGather is another primitive function provided by NVIDIA NCCL. We call this function when we are working with multiple nodes and each node has part of our data, but we want to gather these data across nodes. So in this example, we have four nodes. Each node contains part of our array or data or structure. To gather all these parts, each node will call AllGather. After calling AllGather, every node will have a copy of the entire data. Since this operation is the most important for FSDP, I'm going to present it multiple times using different toy examples. In this figure, we start with an FSDP unit that has four parameters. Basically, this is our flat parameter structure. In this example, we have four GPUs. So we shard the flat parameter onto these four nodes, as you can see here. The first GPU will have weight number 1, while the second GPU will have weight number 2, and so on. Now, in order for a GPU to perform a feed forward on a mini batch, it needs to gather all the weights from all GPUs to perform this operation. It is important to note that we are not gathering the entire model. The entire model is too big to fit on a single GPU. We are gathering a single FSDP unit. After all gather, each GPU can perform its forward or backward operation independently. Once the operation is complete, every GPU will keep its own shard only and free the other shards from the other GPU. Basically, each GPU returns to its initial state before the all gather operation. This is another illustration for the all gather operation using a flat parameter with 16 parameter in it. After sharding, every GPU will be responsible for a single parameter. And when using an all gather operation, we are going to gather all of these parameters again on all GPUs. Another important point that I want to emphasize here is that we never gather the entire model on a GPU. We do all gather per FSDP unit to perform a forward or a backward path. Once the operation is complete, each GPU will freeze the shards from its peers. Another way to put this, the memory requirements for FSDP are proportional to the size of the sharded model. The sharded model basically means that after sharding, every GPU will keep a certain part of the model plus the size of the largest fully materialized FSDP unit. The largest fully materialized FSDP unit means after gathering that FSDP unit across GPUs. This is another figure that shows all gathered during both forward and backward passes. To perform a forward path on FSDP unit number 1, which is this one here, we gather the full parameters, we do the feed forward, and we free the peer shards. The same process happens during the backward pass, as you can see here. This figure shows a complete forward and backward passes on an entire model. It is important to note that we can pre-fetch shards from other GPUs while we are performing a forward pass to better utilize our GPUs. As you can see here, we start all gather on FSDP unit number 0. Once we have gathered FSDP unit number 0, we do the feed forward on that unit, feed forward unit 0. At the same time, the FSDP will prefetch the shards of FSDP unit number 1 to better utilize our GPUs. Again, once all GPUs have FSDP unit number 1, they perform the feed forward on that unit. Once the feed forward is complete, we free the FSDP unit number 1, as you can see here. All that is happening while FSDP is gathering the FSDP unit number 2. And again, once we have this, we just do the feed forward and so on. This all gather for unit 2. This is because we are now preparing for the backward pass, which I'm going to illustrate next. So far, we have covered FSDP unit, sharding, and all gather. Now, the final operation we need is reduce scatter. We will need this operation during the backward pass. Again, reduce scatter is another primitive function provided by the NCCL. We call this function when we are working with multiple nodes and each node contain a different set of data. You can think of this as different arrays or different lists. Now we want to reduce some these arrays, but we want to scatter the results on different nodes. In this example, we have 4 nodes and each node contains, let's say, an array of numbers. If we perform all reduce, we will sum these arrays and broadcast the entire results to all nodes. And this is not what we are looking for. Indeed, we want to reduce some these arrays, but we want each node to have part of the result and not the entire result. And that's why we are using reduce scatter and not all reduce. Now let's see how FSDP uses reduce scatter during backward pass. In this toy example, we have a toy FSDP unit with 4 weights, and we are about to perform the backward pass. Before performing the backward pass, FSDP will first perform all gather to gather all the weights from all different nodes or GPUs. I'm assuming that we have already performed the forward pass and we have a loss value. To compute the gradient, we will call loss to backward. Now, every GPU will have a gradient, as you can see in this figure. It's important to note that different nodes will have different gradients for the same parameter. For instance, the first GPU will have gradient G11, while GPU 2 will have gradient 21, and so on. Indeed, all these GPUs have the same weights, as you can see here, but they have different gradients. And the question is, why do they have different gradients? I'm going to give the answer to this question, but if you don't know the answer already, please pause this video and think about it for a few seconds. Okay, so all GPUs indeed have the same weights. So as you can see here, they are indeed have the same weights, but they are operating on different mini batches. And because of these different mini batches, every GPU will have a different gradient. Now we want to update the weights of our model. In these two examples, as you can see, every GPU is responsible for a certain weight. So GPU 1 is responsible for the first weight, while the GPU 2 is responsible for weight number 2, and so on. To update these weights, we want to reduce the gradient from all these nodes, but every node is interested in part of this reduce result. And this is basically why we use the reduce scatter operation. Reduce scatter operation will sum the gradient from all these nodes. Then it will scatter the result on different nodes so that each node will get the part it is interested in. So node number 1 will get the summation of the gradient of 1, weight number 1 from all nodes, and node number 2 will get the summation of that gradient, for the second weight, and so on. Now that we have covered all the details for FSDP, I hope this figure makes sense and every operation is clear. Since I already covered the forward pass, I'm going to focus on the backward pass. The backward pass starts with all gather operation at this point here to gather the weights for FSDP unit number 2. This is the last FSDP unit. After gathering the weights, FSDP will perform the backward pass number 2. And now every node has the gradient from its mini batch. So FSDP will perform the reduce scatter operation to reduce and scatter the gradient across GPUs. In parallel, FSDP will free the parameters of FSDP unit number 2. Then we need to perform backward pass on layer number 3. Please note that layer number 3 belongs to FSDP unit number 0. And that's why we are doing here backward pass on layer number 0. One thing that is important to note here is that unit number 0 is never freed previously. Like here you see like FSDP unit number 1 has been freed, FSDP unit number 2 has been freed, same for unit number 2, but FSDP unit number 0 has never been freed before. In fact, FSDP unit number 0 is always treated differently. It is always gathered when we start the forward pass, and it is always freed at the end after performing the entire backward pass. Basically, this FSDP unit is treated differently than any other FSDP unit. After performing the backward pass on layer number 3, we want to perform the backward pass on FSDP unit number 1. So first we are going to gather unit number 1 from all nodes. Then we are going to do the pass on unit number 1. Once the backward pass is complete, we can now free unit number 1 and perform the reduce scatter on unit number 1. I believe there is a mistake in this figure. This reduce scatter number 1 block should be shifted after the backward pass of unit number 1 to be basically shifted to this point. This is basically similar to what is happening here between the backward pass number 2 and the reduced scatter number 2. In all events, once we are done with the backward pass on unit number 1, we then perform backward pass on layer number 0, which belong to unit number 0. Once we are done with this backward pass, we will free unit number 0 and reduce scatter the gradient of unit number 0. This is basically where we finalize this a single training iteration. So the main goal of this video is to explain how FSDP works. It is not a difficult process, but it has many moving technical parts. So I hope this video helps someone understand how FSDP works. Before wrapping this video, I want to quickly cover when to use FSDP and when not to use FSDP. FSDP makes sense when we are training large model with billions of parameters. This is different from when we are using distributed data parallel. In distributed data parallel, we assume that you can fit your entire model on a single GPU. In contrast, FSDP is designed for situation where your model is too big to fit on a single GPU. And in this scenario, FSDP will divide your model across GPUs. Of course, this is not for free. There is no free lunch. FSDP involves many communication between your GPUs. Basically, when using FSDP, you will be trading GPU memory for time. Another reason to use FSDP is that PyTorch framework has made it easy to switch from DDP to FSDP. There are two code changes required to make that switch. First, you need to wrap your network using FSDP instead of DDP. Also, please keep an eye on how you load and save your checkpoint. On the left-hand side here, a code snippet creates a DDP model, while on the right-hand side, a similar code snippet creates an FSDP model. As you can see, it is easy to switch between DDP and FSDP. This wrapping policy tells FSDP how to create the FSDP units. PyTorch already provide generic wrapping policy. Generic policies are not optimal, but they should support any model you are using. Beside the constructor, as you can see here, please keep an eye on how you save and load your checkpoints. When using FSDP, no single GPU has a complete picture of your model. So you will need to gather the parameters from different GPUs before you can save a checkpoint. PyTorch already provides a way to do so in an easy way. You don't have to worry about it. Just don't forget about this part. Now it's time to wrap this presentation and review reasons for not to use FSDP. FSDP is developed for billion size models. So as a rule of thumb, if your model is, let's say, less than 100 million parameters, you probably shouldn't use FSDP. There is one point that I already mentioned at the beginning of the presentation, and I want to mention it again here, is that FSDP reduces the memory consumed by the parameter and the optimizer, yet the network intermediate features and activations during training will consume a lot of GPU memory as well. So it's important to keep an eye on the amount of memory consumed by these activations. And one way that we can reduce our GPU memory for this activation is by simply using other techniques like activation checkpointing or changing some layers into basically using reversible layers. Another reason for not to use FSDP is that it has been recently in mid 2023 supported by PyTorch. If you want to use, like, you will need PyTorch 1.13 in order to use mixed precision with FSDP. pfloat 16 requires certain GPU families like Ampere. If you want to use a mixed precision float 16, you will need to change your code from using grad scalar to using sharded grad scalar. Also, when using FSDP, we are, as I mentioned before, like we are trading GPU memory for time. So we will be incurring more communication cost across our GPUs. Another reason for not to use FSDP is that FSDP comes with extra overhead per architecture. I hope that you now understand that when using FSDP, we need to create FSDP units. And to create these units, we need to provide a policy for the FSDP constructor, as you can see here. I already mentioned that PyTorch provide generic wrapping policy, but these are generally less efficient. So if you plan to use FSDP, you should create your own architecture specific policy. For instance, if you are using a transformer model, you will need to specify the layer class to create FSDP units. The final reason for not to use FSDP is that partial fine-tuning is non-trivial. PyTorch assumes that when you are using FSDP, you are either training the entire model or fine-tuning the entire model. If you want to freeze some layers and fine-tune the other layers, this is possible, but you will have to use some custom code to implement this feature. Finally, these are the resources that I use to create this presentation. I'm going to make this presentation public and leave the link in the description of this video. If you are still listening till this point, I want to thank you for your patience, and I hope you enjoyed this video.